Okay. Hi, I'm Laura. Sorry about the voice. I've got a cold. Probably given it to everybody else too. Sorry. So my project is developing different microscopy techniques to study lithium-ion battery degradation mechanisms, and I'm working in collaboration with Johnson Matthey and with Beverly Higgson at Sheffield University. So why are battery degradation mechanisms a problem? So microstructural degradation, such as solid electrolyte interface formation, and volume changes can cause a reduction in lifetime and capacity. In particular, my project is currently focusing on high voltage battery materials, in particular lithium cobalt phosphate, and as you can see, the capacity utterly fails after 10 cycles, which is frankly useless for any kind of commercial battery. The problem with that is that with high voltage cathode materials is that they operate over the breakdown voltage of current electrolytes, and as a result form these solid layers on the surface which blocks lithium from going out, and also these layers are unstable. The key thing about this process is that it is both a nanoscale process and an active process, so it's actually quite difficult to characterize how this happens. In situ transmission electron microscopy, which is the technique I'm trying to develop, has potential to enable us to study this. So transmission electron microscopy is where you fire electrons through a sample, which gives you both structural and chemical information about the sample on the nanoscale. And what I mean by in situ transmission electron microscopy is I can charge and discharge the sample whilst we're imaging. So in theory, you should be able to view the SEI layer being formed. This has a number of advantages. For example, you gain transient information which you otherwise wouldn't get if you were to decrypt a cell, and also you can directly image things such as the SEI layer. However, you're firing 300 kilovolt electrons at a sample, and that's going to cause many a problem. And so the major problem with this technique is trying to identify what's happening because of the electron beam versus what's happening because you're charging and discharging the battery. So to do this, I have so far irradiated regular battery electrolytes. This is LP30 under a 300 kilovolt electron beam, and as you can see, we weren't quick enough to get a picture of the black electrolyte, and it instantly precipitated. And as we continued with the electrolyte irradiation, these precipitates grew and grew and grew, which obviously isn't ideal for trying to do any kind of in situ battery study. So we think we'll be able to optimize the beam current and voltage, as has been done in the literature, to hopefully reduce this damage and actually be able to image these batteries in situ. So in conclusion, in situ TEM has high potential for studying battery degradation mechanisms. My future work will be to try and optimize the beam conditions so I can actually do the imaging without any kind of beam damage occurring, and ultimately to use the system to study degradation in high voltage cathode materials.